Okay, I think we'll get started. So today we're talking about a variety of things that we've sort of started talking about before: weight, normal force. So we've certainly used those concepts before, but we're going to see them in a little bit different light, add this idea of apparent weight. So kind of a hodgepodge of things today. If you're coming from the GNL project, I encourage you to go look at the introductory video for this playlist to see if this is the right sequence for you. Okay, well, we've talked about weight before, and we know that weight as a vector is mass times the acceleration. Here, this vector over the g means 9.8 meters per second downward. And so the magnitude of the weight is mg, and its direction is pointed downward, as we've been using in a number of problems already. Okay, well, let's introduce a new concept here, this idea of apparent weight. And you've experienced this if you've been in an elevator. When it starts to take off, you feel a little bit heavier. When it starts to come to a stop, you feel a little bit lighter. Or you're in a car going over a hill or a carnival ride or something, go up, you feel a bit lighter, and then you come back down and you feel a little bit heavier in your seat. What you're experiencing is your apparent weight, not your actual weight, which is your mass times the acceleration due to Earth. And the apparent weight then is the weight, the actual weight. So the magnitude here is the magnitude of the weight, and then plus the mass times the acceleration in the upward direction. And so this could be positive or negative, so it can contribute to making you feel heavier if this is positive, or contribute to making you feel lighter if this is negative. So let's put this in an example. So let's say we've got an elevator and we're holding on to this 15 kilogram weight, or it's on the floor, whatever. We have to provide a normal force that is equal to the weight of this 15 kilogram object. So 9.8 times 15. So this is the weight right here. Now, let's say the elevator starts to accelerate upward at 0.75 meters per second. The upward acceleration will make us feel like this weight will make the weight feel heavier. So we're going to have to provide more force to counteract that weight. And so let's calculate that. Well, we add this component of the upward force, and we get 158 newtons. Now, I like to use the term apparent mass. It's not really a thing, so it's not a technical thing in physics, but I think we're just more used to thinking about kilograms than we are about newtons when it comes to what that feels like. And so if we take our apparent weight and divide by 9.8, we get the mass equivalent. So it would feel to us like we were holding on to something that was a little over a kilogram. Because of this upward acceleration. So it would feel heavier. All right, well, let's imagine that this elevator starts to undergo free fall. So it just starts falling. Then what happens? Well, now the acceleration is downward. It's in a free fall. We've talked about free fall problems, and they experience a downward acceleration of 9.8 meters per second squared. So if we put this into our formula, we actually get complete cancellation of the weight, and this is what we refer to as weightlessness, or feeling weightless. And so when the astronauts, they can undergo some weightless training without going into space, because you can go up in a big airplane, and then it can basically free fall for a while, go from very high altitude to a lower altitude very quickly. And it's simulating weightlessness up there. Very close to weightlessness. All right, well, let's shift gears a little bit, although we'll come back to this idea and talk about normal force. So we've used normal force already, and that is just the force necessary to keep an object in place in certain situations. So if I'm standing here on the floor, we don't really think much about the floor other than the floor is keeping me here. And so I'm not moving. I have a weight force pointing downward. I thus must have an upward normal force due to the floor pointing upward. Now that force will respond, it's a responsive force, just depending on whatever it needs to do to counterbalance a weight. So if we replace me with a box that's, say, lighter, then the upward normal force on that box is less than it is on me. Now if I come over and I push down on the box, so let's say I push down on this box, then I'm supplying extra downward force, and so the normal force has to grow accordingly in the upward direction. And so if we were to draw a free body diagram for that, we have the weight force, the downward pushing force, and then the normal force will have to counterbalance that. So these two vectors added together must equal this. So we get the normal force is equal to the weight vector and the force vector. Actually, I should have this. Sorry, let me take this in steps. So this is equal to 0 because we have a net 0. Force net is equal to 0. So there's our equation. And so the net force is minus, equal but opposite, the pushing force and the weight force. There, that's better. Okay, well, coming back to this elevator example, then if the weight was sitting on the ground, this 15 kilogram mass was sitting on the ground, and then we accelerate upward like this, then the floor of the elevator would have to provide an additional amount of force for a total of 158, as if it were holding a 16 kilogram weight or mass if it were sitting still. Now, let's look at this in another setting. If we throw an object up in the air, especially if it's a heavy object, we want to kind of cushion that catch. We don't just catch it in place. If it's light enough, we can do that. So when we make the catch, right, this is coming at a certain velocity, and then when we catch it, stops. So it's undergone an acceleration in the upward direction or against its motion. So a deceleration. So we have an upward acceleration causing this to stop. So if we have an abrupt catch, we have a high acceleration. We've just seen here now that would give it an apparent weight much greater than its actual weight. So if it's something really heavy, there's no way we could really hold our arms straight up like this without cushioning it. When we cushion it, the act of cushioning it prolongs that deceleration times, dropping the deceleration. So it may be 10 times longer from the abrupt, like no cushion, to a good cushion all the way down. And so we can diminish this acceleration term and thus diminish the apparent weight and then be able to handle that catch easier. Okay, so that's going on here. Now, of course, before we catch it, we have our hand is supplying no normal force. When we catch it, then our hand is supplying more normal force than the weight. And then finally, when we bring it to a stop, then just sitting here like this, our hand is providing a normal force just equal to the weight. All right, let's leave apparent weight for just a moment, or now, and let's talk about normal force in a ramp setting. And we haven't talked about ramps in a little while. So remember the ramp coordinate system, we rotate the coordinate system so that we call this x prime along the ramp, and then y prime is in that direction. The normal force is always normal to the surface. So it is pointing directly in the y prime direction, not in the y direction, straight up. Now we've learned that the acceleration, so we've seen this formula before, the acceleration down the ramp is g times sine, and then we choose plus or minus depending on how we drew the ramp. So I drew the ramp this way, so negative is this way. If I had drawn the ramp this way, then the positive would have been this way. We would have used the plus sign. So we have to be careful with how we drew the ramp there. The normal force is always in the upward y prime direction, so that's positive, and that's going to be mg cosine of this angle. So let's, it's always good to, with these formulas, to take the extreme. Let's take flat surface. Then theta equals 0. If theta equals 0, then there's no acceleration in the x direction, which makes sense. It's just sitting there. There's no way it would just start accelerating. The normal force, cosine of 0 is 1, so the normal force would just be mg, as if it were a flat floor, right? So that checks out. Now let's take it to the other extreme. Our normal force would go to 0, which is the case because there'd be no, the weight would just fall because it's not the floor, this ramp would no longer be supporting it at all. So it'd be 0. And then the acceleration, sine of 90 degrees is 1. So the acceleration would be negative g coming down in that direction. All right, well, let's just do a quick example. Let's say we had a box of, and let's put this on ice first. So we've got a frictionless surface at first. So we have, say we're given it's 80 kilograms and it's 27 degrees. Then we will calculate our acceleration here now based on our formula. Minus 9.8 sine of 27. That is negative 4.45 meters per second. So it will start to accelerate this way. Not as fast as free fall, of course, as we would expect, but it'll accelerate this way. And then the normal force that's being provided, we can calculate that as well. So that's 80 times 9.8 cosine of 27 degrees. So we get a normal force there. Now, let's change this. Let's make this problem a little bit harder. Let's say this is not ice anymore. And let's say the box doesn't slide. So it's sitting there. It's in stable equilibrium. And it is static, right? So the net force here, in this case, the force net is equal to 0. Okay. Well, how does this work? We have this downward force that we just calculated. Here, well, we have the acceleration. So if we take mass times this, we can get it this direction here is mass times this acceleration in this direction. That was the net force when this was on ice. Now, if we are sitting here, there must be a counterforce. Otherwise, we'd be accelerating down like we did with the ice. So there is indeed a counterforce, and that's the friction force. Like that. And so the net force is 0 here. The net force is now 0. And how do we calculate this friction? Well, we haven't learned how to calculate friction yet. This arrow has to counterbalance that arrow. And so the friction here equals minus, equals mass 80 times 4.45. Now in the upward direction, I think that's about 356 newtons. And I want to be a little bit careful here. I was a little sloppy. I was drawing this on the free body diagram. We do indeed have a free body diagram. Let's review the free body diagram. There's no downward force here, right? That was my mistake. I shouldn't have put that on there because that isn't there. So we have this frictional force. We have this and this. We don't know how to calculate that frictional force yet. Next lecture, we'll learn how to do some calculations of frictional force. But we can get it in this case because it would have to counter this net force as if the friction wasn't there. So we were able to, by multiplying by mass of this acceleration, get the force down the ramp. So the friction has to exactly counter that. And so that's how we can do this. So our calculation is correct. I should not have drawn that arrow on the free body diagram. This is the free body diagram here. Okay. So this gives us a clever way of calculating friction using our ideas from equilibrium from the last lecture. But like I said, we will learn how to calculate friction based on something called the friction coefficient, which has to do with which two types of surfaces are in contact trying to slide across each other. And we'll take that up next time.